we're going to take a look at some more advanced projectiles. And this is pulling on what we did before with projectiles, but now saying if there's an angle, what changes? So what we mentioned before was treating those two things completely independently. They're actually the horizontal and vertical components of the velocity. Or of position, or of acceleration. So if we're dealing with components, we can use trigonometry. So your most basic example is just going to be this right triangle right here, where we know that this is our x quantities, this is our y quantities. We'll have some angle, and this is the sum, or the actual value. So for example, v, the actual velocity, the total velocity, will equal vx squared plus vy squared. A will equal a sub x squared plus a sub y squared. So in other words, the velocity in the x direction plus the velocity in the y direction, because they're always going to be at right angles to each other, we use the Pythagorean, sorry, this should be square root. We use the Pythagorean theorem to combine them and solve for the hypotenuse. Likewise, if I knew the velocity and I wanted to find Vx, I could write that as Vx equals the velocity times the cosine of theta. Vy would equal v times the sine of theta. Or if you're using phi up here, it would just be switching these two because it would be opposite our hypotenuse. Where do these come from? They come from knowing that sine of theta should equal to the opposite value, which is the Vy, divided by the total velocity V. So then if I just multiply both sides by V, I get my V sine theta. Similarly for cosine, I get the other. If this is something that's a little weak for you or tricky, ask me in class and we'll talk through it together. I'll probably pull a small group of you. But if this is something you're comfortable with trigonometry, this should, if you pause, look over it, track it, it should make pretty clear sense. The same thing would be true for accelerations. Ax would equal a cosine theta. Ay would equal a sine theta. And so this is where all the stuff we were talking about before. And then if you get, your final velocity in the x direction, your final velocity in the y direction, but you want to find the sum, again, just use the Pythagorean theorem. So we're not going to do a whole lot of problems solving things like this, but I just wanted to show it to you so you kind of see where it comes from and how it works. If you went on to AP Physics, you would definitely expect it to do this sort of thing. If you went on to university level physics, you'd definitely be expected to be able to work with this sort of logic. But I want to just introduce it, give it as kind of a thing to play with, and have you start to think about what happens with projectiles. So here's a question as an example. Which travels farther, a projectile launched at an angle of 30 degrees or one launched with the same speed at an angle of 60 degrees? So what we're looking at is basically this setup right here. So we've got an initial angle theta, and it travels and hits the ground again. So I'm going to start by just sketching out the generic equations, the generic depictions, and setting up some generic equations. And then we'll work about details. So Vx, Vy, and theta. So what we want to find is this distance right here, delta x. And we know that delta x should equal to Vx times the change in time. How do we know that? Well, because we know that the velocity isn't going to change in the x direction because there's no forces pushing or pulling it backwards or forwards, no acceleration. So the velocity is constant, and this is actually coming from the plus 1/2 a delta t squared ax, but that whole last term is 0. So I know delta x, I know vx, I'll be able to find it from my angles here. But I don't know delta t, so let's try and solve for that using our delta y. Delta y should equal vy delta t plus 1/2 times negative g times delta t squared. Because we know in the y direction, the vertical acceleration is g, is the acceleration due to gravity. The y velocity we know is going to be sine theta. Now what ends up getting a little bit tricky here that we'll see is we're going to have to do some clever math or realize that if I start at this height and end at this height, delta y is 0. So what that means is I can do some rearranging here and get vy delta t equals 1/2 g times delta t squared. And I could plug in the known v, that should be v sine theta and v cosine theta, but I'm leaving them as vx and vy for now because it'll be a little easier to work with. A delta t can cancel from both sides, and I get that delta t is equal to 2 vy over g. Make sure, yep. So then I know that delta x is equal to vx times 2 vy over g. Delta x is equal to v cosine theta and then v sine theta over g, and I'll pull the 2 out front. So delta x equals 2 v squared divided by g cosine theta sine theta. And so if we go in and we plug in the sine and cosine of those angles, you'll notice something interesting pop up, unless I've gotten too far ahead of myself. And you'll find that cosine of 30 sine of 30 and cosine of 60 sine of 60 should give you the same values, right? I'm just double checking because I am second guessing myself. So we're just going to go make sure we're looking at working with degrees. And sine of 30 cosine of 30 is going to give us square root 3 over 4. So delta x for 30 is equal to 2 v squared g square root 3 over 4. Delta x of 60 is equal to, like I said, I'm pretty sure this is the same, but I'm a little tired, so I want to make sure. And yes, it is in fact the same. 2v squared over g square root 3 over 4. So actually, both of these travel the same distance. But since we derived this general equation for the range of a, whoops, not sure what happened there. Since we derived this general equation for the range of a projectile, you can see what numbers are going to get bigger and smaller, and you can compare different angles and find ones that do vary.